Hello friends, welcome to the channel Physics by IITians. We are back with another interview question, and these questions were asked in IIT Madras PhD interview. The questions are: draw particle in a one-dimensional box whose wave functions can be both sine and cosine, that is a symmetric box potential, and you have to draw the particle inside that box. The second question is: plot wave function for particle in a one-dimensional box for ground state and first excited state. And the third question is: why excited state has more energy compared to ground state for a particle in a one-dimensional box. So I think this is a very deep concept in quantum mechanics, and this is a very basic concept actually, and you should understand it in a deep manner. That's why I have decided to tell you each and every physics of the wave function and the energy states here for both for the symmetric and the asymmetric case. So please watch the video carefully. First, you should know about what is the one-dimensional box potential. One-dimensional box model is the infinite potential well or the infinite square well, where the particle is free to move in a small space surrounding by impenetrable barriers. That is, suppose you have a potential, and look here, this is a potential box. Here 0 to L, so L is the length of the box, and within the box the potential is 0, and outside the barriers the potential is infinite. So the wave or the particle cannot penetrate this infinite potential barrier. So barriers outside a one-dimensional box have infinitely large potential, while the interior of the box has a constant or zero potential. Now the potential, this kind of potential can be of two types. One is the asymmetric potential and another is the symmetric potential. What is asymmetric potential? Asymmetric potential has the nature where V of x equals to infinite for x less than 0, V of x equals to 0 for x 0 to a, V of x equals to infinite for x greater than 0. Suppose this is the x variation, that is from 0 to a. So from 0 to a, V of x is 0, that is 0 potential, and this or whether this side or this side, that is x is less than 0 or x is greater than a, Vx is infinite. What is the symmetric potential? Symmetric potential where V of x equals to infinite for x is less than minus a by 2, 0 for minus a by 2 to plus a by 2, and infinite for greater than a by 2, means minus a by 2 to plus a by 2, Vx is 0, and whether x is less than minus a by 2, this is also infinite, this region, or greater than plus a by 2, this region is also infinite. Now to find out the nature of the wave function, we should know the psi x, that is wave function value for this kind of potential, that is box potential. We should find out the psi value for the asymmetric and symmetric, both type of cases. I will first tell about the asymmetric case and then I will tell about the symmetric case potential. So for the asymmetric box potential, we take the box that is of a length of 0 to a. So we are choosing this diagram, or we are choosing this potential. Okay, so it is from 0 to a, otherwise it is infinite. So V is 0 means the potential is 0 inside the box. So the Schrodinger equation, we have to take only the kinetic energy term. So d2 psi dx2 plus k square psi equals to 0, since it is one dimensional and we are considering the potential variation along x only. Where here, so k square is 2me by h cross square. So the equations, solution of the equation is oscillatory, that is psi x can be written as a sin kx plus b cos kx, where a and b are here constant coefficients. Now how to find out constant coefficients? Constant coefficients can be found out from the boundary conditions. Now what will decide the boundary condition? The boundary conditions will be decided by the potentials. Okay, so the nature of the potential will decide your boundary conditions, and that will from that condition you can find out the constant in any equation. So what are the boundary conditions? We have taken the potential box of length 0 to a, that is a. So at x equals to 0, the potential is infinite. At x equals to a, the potential is also infinite. So the wave function at x equals to 0 or x equals to a should vanish because it cannot penetrate the infinite potential well. So psi at x equals to 0 should be 0, and psi at x equals to a should also be 0. What will give these two conditions? These two conditions gives that psi for x equals to 0, 0 will give as b equals to 0, because this term should be 0 at x equals to 0, and for psi at x equals to a, this term should be 0. So here a sin k equals to 0. So sin k, a sin k 0 means k n a. This cannot be 0. This is the amplitude of the wave function. So this can only be 0, and this can only be 0 when k n a equals to n pi, where n equals to 1, 2, 3, etc. up to infinite. 1, 2, 3, 4, 5, 6. So why is the n equals to 0 has been excluded? Because n equals to 0 means this psi is 0. Now wave function is 0 is meaningless. So n can only start from 1, 2, 3 integer values. Now we should understand what should be the energy value, energy eigenvalue. So k square is 2me by h cross square. So k we get as n pi by a. So put the value n pi by a whole square equals to 2me by h cross square, where we get en equals to h cross square pi square by twice ma square to n square, or n equals to, for n equals to 1, 2, 3. Here, look here, this is the quantum mechanical way of or philosophy to think that here you are seeing this expression of the energy, eigenvalue energy, that is dependent on n square or quantum numbers. N is discrete here, that is 1, 2, 3. The certain values are possible for the energies. Earlier in the classical mechanics, the energy can be anywhere, the energy can lie anywhere, but whenever you are going or you are entering into the quantum regime, these energy values are not now continuous, rather the energy values are now discrete. Okay, so n equals to 1, 2, 3 will decide the energy levels for E1, E2, E3, E4, etc. So what is the conclusion? Conclusions are the energy is quantized, only certain values are permitted, states are bound states, and energy spectrum is discrete. What is the difference between the two consecutive energy levels? To find out En plus 1 and find out En, and then take the difference of them. So how to find out En plus 1? You just put En plus 1, you replace n to n plus 1 here, and also n plus 1 whole square put here, and then take the difference and you get the value as 2n plus 1. And in the classical regime you get that the ratio of En plus 1 minus En divided by En equals to or tends to 0. Now what will be the wave function? The wave function will become, after normalization, we can find out this constant a is root over 2 by a. So a wave function becomes root over 2 by a sine n pi x by a, where n equals to 1, 2, 3. The wave functions can have infinite number of solutions depending upon the value of n. Now what will be the wave function for the symmetric potential case? The symmetric potential, the nature of the potential v of x will be symmetric, that is whether it is at v of minus x at the point minus x, it will become v of x. The asymmetric potential where v of minus x equals to v of minus v of x, here v of minus x is equals to plus v of x. The wave function is also bound state, and there can be even or odd. This case only sine values, that is sin n, is only the function root over 2 by a sine n pi x by a, where n can take value 1, 2, 3, etc. But here there will be the change in the wave function, and the change in the wave function will become, it can be both sine and it can be both cosine depending upon the n value. For n equals to odd, that is n equals to 1, 2, 3, 1, 3, 5, 7, etc., the wave function will become root over 2 by a cos n pi x by a, and for n equals to 2, 4, 6, 8, that is the odd even numbers, sin n, that is wave function, will become root over 2 by a sin n pi x by a. So look here, compare, I want you to compare these two wave functions. Here this is the asymmetric potential, okay, only the sine wave functions, and here this is the symmetric potential. Okay, this is a symmetric potential, this is a cosine, and this is a antisymmetric wave function, not potential. This is the symmetric wave function, and this is the antisymmetric wave function. We will understand it clearly when I tell you, I will show you the pictorial diagram. So how did you get this? Why these potentials that is for n equals to odd this is cosine, and for n equals to even this is sine, because of the boundary conditions. Though as these boundaries are symmetric boundaries, you solve the Schrodinger equation the same way like the previously, and you put the boundary conditions, and you will find that the one will be 0 for some values of n, and the other term will be 0 for some values of n. So for n equals to odd, only cosine term will survive, and for n equals to even, only sine term will survive. So now we'll understand the wave function nature and the energy levels. So look here, this is the wave function, that is psi n equals to root over 2 by a sine n pi by a n pi x by a, or for the, that is the potential box, particle in a potential box. This is for the n equals to 0 level, n equals to 1 level, because n equals to 0 is not allowed, it will lead to function psi wave function is 0. So the lowest term quantum number is n equals to 1. So n equals to 1, the wave function is this. N equals to 2, the wave function is this. N equals to 3, the wave function is this. Now we shall understand it very thoroughly. Let me show you this diagram first, which I can show here. Look here. This is a diagram for a symmetric potential or asymmetric potential, that is particle in a box. The question is, draw the diagram or draw the particle inside the potential well or potential box. So this is for n equals to 1. This is for n equals to 2. These are the probability. Whenever you are telling to show the particles, you can tell them these particles, they will be expressed in terms of the probability distribution. So you have to show the diagram, this schematic diagram here. And when in terms of the wave function, look here, see here, this is another diagram. This is also beautiful diagram. Look here, this is the particle, and it can have the wave functions. This is the particle. So this is the particle A. This is another diagram, that is for the ground state. This is for the first excited state, for the second excited state. There are nodes, and here, look here, the nodes at the boundaries. Now you have to understand the similarity between the particle in a box, one dimensional box, and the particle or the sound wave, vibration of a string. How do you understand it? Suppose at the boundary, this particle or this matter wave cannot penetrate. So at this boundary, there should be nodes, and these nodes or this boundary condition will lead this particle or leads these energies to be discrete, and only certain energy values are allowed. Now compare the philosophy with the de Broglie, because the particles that are confined, they have finite momentum or finite wavelength, because according to de Broglie, P equals to h by lambda. Now here only certain lambdas are allowed, because here, look here, these are as like they are forming a standing wave or stationary waves, because this wave will return and it will come back, and then it will go and it will return. I mean, it cannot penetrate, so at this boundary it will reflect and it will come back. Then again with this boundary it will reflect and it will come back. So again with this, from this boundary, so it will happening. So whenever there is this kind of phenomena happening, we all know that there will be the stationary wave formation, that is the wave is not losing any energy, and it is consisted of the de Broglie model, because he also proposed that whenever if we consider the hydrogen atom model also, only those wavelengths are allowed which will interfere constructively, and those only nh by 2 pi, that is the multiple number of nh cross, those will obey the quantum condition rule, quantization rule. So this is for the hydrogen atom case. And here for the particle in a one dimensional box, the same thing you can understand, that those waves are allowed only who are forming the stationary states, and the stationary states are absolutely stable states, because there is no transmission of energy. So, and here is a beautiful analogy between the string motion and the particle in a one dimensional box. and it is its probability distribution. Look here, whenever we are the nodes are actually very important here, because whenever you want to draw the cartoons of the wave function, first you need to know the nodes, and you find out if you find out the nodes now, then you can also can understand the what are the distribution about the nodes, whether they are symmetric, whether they are not symmetric, and it will tell us lot about the wave function. Look here, suppose you are taking this wave function, and here look here, this one here, this is the ground state, or you are plotting the ground state wave function. So this is suppose the 0th point, and look here, the wave function here or here, it is symmetric when you take the boundary as minus a by 2 to plus a by 2. Now the similar thing you take it here, and you look here, the wave function is not symmetric, it is antisymmetric. Next, for the third state, n equals to 3. Look here, the wave function is again symmetric because it is symmetric. We can see it, observe it, okay? So these are the nodes can tell you whether the wave function is symmetric or not, whether the potential is symmetric or not. So the nodes are very much important in quantum mechanics. That's why the cartoon of the wave functions are always instructed to draw. It's a very common question that you can be asked anytime. Now we should understand about the energy, that why the energy levels also increase with the increase of n. Here from mathematically we can also understand that energy level is En is directly proportional to n square, that is, and n is starting from 1, 2, 3. Now why n is not minus 1, minus 2, minus 3? Because again the wave function will be negative, so we will take only n the positive integers. Now here mathematically for n is increasing, so En will be also increasing, where E1 will be n, this one, suppose we are taking this as E1, so n equals to 1, it will be E1. For n equals to 2, that is E2 will be n square, for that is the 2 square into E1, that is 4E1. For n equals to 3, that will be 9E1. So this energy will be increasing, and the about with the increasing of n value, that is quantum number. Now how do you understand it physically? You can understand, look here, this is the n equals to 1 level, and this is for the n equals to 2. Here if you think this is the wavelength, then this is the wavelength of lambda by 2, and this here, this is the wavelength of lambda. So here you can understand that this much lambda by 2 is here, and I mean the frequency is here much more greater than the frequency here. If you find in terms of the wavelength, look here, this is wavelength, that is lambda by 2, and here this wavelength is of lambda, or you can write it as 2 into lambda by 2, because the constant interference here happening at the multiple wavelength of lambda by 2, that is multiple integer of lambda by 2, that is m into lambda by 2 is the constructive interference condition. So the constructive interference are forming the stationary waves. So in view of the wavelengths, if we show here, then if we look here, observe here, we can understand that for n equals to 1, this is lambda by 2, and for n equals to 2, this is this amount. So the wavelength here, the frequency has been increased here also, and whenever you are taking this one, that is m into lambda by 2, that is here m will be 3, that is this is 1 and this is 1, 3 into lambda by 2, or you can write it as this is lambda by 2, this is lambda by 2, and this is lambda by 2. So total 3 into lambda by 2. So within that region the frequencies are increasing. So the frequencies are increasing means the energies are increasing. So with the level, the permitted levels, the energy levels will be automatically increasing because of this quantum condition, that is n equals to 1, 2, 3. You are increasing the energy levels means you are increasing the quantum number, and due to that quantum number increasing, what is happening to the higher state, the inner wavelength or is decreasing, or the frequency of the wave particle is increasing. So this is a consequence of the increase of the energy levels. So this is a physical aspect, then you can understand. And also one more thing that is very important, that En, n is 0 is not allowed, means En, that is energy of the particle, cannot be 0. The ground state is minimum, having the minimum energy of h cross square pi square by twice m square, and this is directly coming from the Heisenberg uncertainty principle, that the ground state energy cannot be 0. If ground state energy is equals to 0, that means the particle is at rest. So particle is at rest means its momentum, you can find its position also exactly, you can find its momentum also exactly, but it's not possible because according to Heisenberg, the delta x and delta p should have a minimum uncertainty of h cross by 2. So this is the minimum motion of the particle is needed. So that's why this is called the 0 point energy, and therefore it reflects the necessity of a minimum motion of a particle due to localization. And this 0 point energy occurs in all bound state potentials. So I think you understand, and also if you understand it, the 0 point energy in the macroscopic world, though it is infinitesimally small, because the quantum effects will only be observable precisely, or in the infinitesimally small region, that is the atomic level, microscopic level, you can macroscopic world we cannot see it, observe it, but it has non-negligible, because the microscopic system, we cannot neglect the size of this uncertainty. So that's why we cannot observe this 0 point energy in the macroscopic system. So these are all we have learned, that these are the wave functions, and this is actually, this is a GIF at a certain instant of time. This is the motion of the wave function. It is going, coming back, then going, reflecting, coming back. So it will make a standard wave formation. So look here, the beautiful analogy between some common physical aspects. We get standard stationary waves for the sound waves. We get stationary waves for the electromagnetic waves we confine within a wall, that has also been discussed, and we also get the same nature whenever the particle is within the one dimensional potential box. So can you relate this, the photons or the lights or the sounds or the particles? But though this light or sounds we can observe this very easily, but here the material particle, for in case of electron or like microscopic objects, we cannot see it, because this will be negotiable only at the atomic scale or quantum scale. So I suggest you to think more about this and relate the things, the quantum, classical, electromagnetic theory, sound, waves, electromagnetic waves. So everything you should understand how to connect them to get a detailed analogy of different topics. Actually, they are not different. They are quite symmetric, and you are the one who is responsible to find out the symmetry of the different branches of physics. I hope you can understand today's video. If you like this video, don't forget to like it. Don't forget to share with your friends. Also, don't forget to subscribe the channel. We have a Telegram channel. Don't forget to join the Telegram channel, because we put quiz questions every day. And if you want to help us, you can help us by clicking this given in the description box. Thank you.